Hey everyone, and welcome. Today we are tackling the most famous, the most iconic equation in all of science, E equals mc². We all think of it as the crown jewel of Einstein's theory of relativity, right? But what if that whole story isn't quite right? What if it's not a result of relativity, but actually its most crucial prerequisite? In this explainer, we are diving deep into a really fascinating argument from Chapter 3 of Newton and Relativity that pretty much turns the history of physics on its head. Let's get into it. Just stop and think about that for a second. What if the one equation that basically defines modern physics could be proven using nothing but classical, old-school principles, without any of the mind-bending stuff like time dilation or warped space-time? Well, that's the wild possibility we're going to explore right now.
Okay, so first things first, we need to talk about the official story. We have to understand the established belief, the dogma that has been taught to physicists for more than 100 years. Yeah, this is the way we're all taught to see it. E equals mc² is supposed to be the final prize you get after this long, complicated journey through the math of relativity. It all starts with things like Lorentz transformations, the tricky equations that say time can slow down and space can shrink. And this creates a kind of catch-22, doesn't it? You're told you can't get to the famous equation without first buying into all the bizarre, paradoxical ideas of the very theory it's supposed to come from. And because of that, the whole idea of the equation's origin in relativity has become, well, a dogma. The source material points out that if you even suggest you can prove mass-energy equivalence with classical physics, you're often met with actual irritation. The idea is so deeply ingrained that challenging it seems, almost heretical. But this is where the story gets really interesting. We're about to uncover a secret that's been hiding in plain sight, and it dates all the way back to 1884. And here is where the plot just thickens beautifully. This quote from the legendary physicist Max Born says that Einstein himself came up with a simple proof that doesn't use any of the heavy math from relativity. Just think about that. The man who gets all the credit for the equation also showed us a way to get there without his most famous theory. So what's the secret sauce here? It's a classical physics idea called a Poynting theorem from way back in 1884. All it really says is that light, an electromagnetic wave, carries momentum. It can literally push on things. This idea existed decades before relativity was even a glimmer in Einstein's eye. And believe it or not, it is the key that unlocks this entire puzzle. Okay, so let's see how this all clicks together in our first proof. We're going to walk through a really simple thought experiment based on this idea of radiation pressure, light that can push. All right, check out this setup. It's about as simple as it gets. A perfectly closed system. We've got two identical bodies, K1 and K2, just sitting there, not moving. No outside forces at all. And this means we have a golden rule, a non-negotiable law of physics. The system's center of mass cannot move. It has to stay absolutely fixed in space. Okay, now let's make something happen. Imagine the first body, K1, shoots a little burst of light over to K2. Because light has momentum, K1 gets a little push backward. It recoils. And boom, suddenly we have a paradox. If one of the bodies is now moving to the left, shouldn't the whole system's center of mass be shifting? But our golden rule says it can't. So how in the world is that possible? Well, it turns out there's only one possible solution, and it's kind of mind-blowing. For that center of gravity to stay perfectly still, the act of emitting light must change the object's mass. K1, the body that recoiled, has to lose a tiny, tiny bit of mass. And since we're in a closed system where nothing can just disappear, K2 has to gain that exact amount of mass when it absorbs the light. The entire thing boils down to three simple classical relationships for time, mass, and momentum. And this is the magic moment. Don't worry, we're not going to get bogged down in the algebra here, but conceptually, it's just a few simple steps. You combine the classical equations for the light's momentum and the time it takes to travel. Then you plug in the change in mass that's needed to keep the center of mass perfectly still. When you link these purely classical ideas together, the conclusion is just unavoidable. The tiny bit of mass that's lost is exactly equal to the energy of that light beam divided by the speed of light squared. And just like that, we've arrived at E equals mc². And we didn't touch relativity once. Okay, I hear you. Maybe that was just a one-off, some kind of clever thought experiment trick, right? A fluke? Well, let's look at a second, completely independent proof that uses a totally different classical phenomenon, the Doppler effect. So this time, the setup is totally different. We've got just one body, and it's moving at a nice, slow, non-relativistic speed.
Then at some point, it spits out two identical photons in opposite directions, one forward, one backward. This whole thing is based on classical electrodynamics, completely separate from our first proof.
Now, if you're just standing there watching this happen, what do you see? Well, because of the classical Doppler effect, like how an ambulance siren sounds higher when it's coming towards you, it's the same idea with light. The photon shot forward appears blue-shifted, meaning it has a higher frequency and more energy. The one shot backward is red-shifted, lower frequency, less energy.
Right. Another one of those unbreakable rules. Momentum has to be conserved. Now, you'd think shooting two things out in opposite directions would cancel out perfectly. But because of the Doppler effect, that blue-shifted photon going forward packs a little more punch. It has more momentum than the red-shifted one going back. So how do you balance the books? The only way to make the math work and conserve momentum is if the body itself lost some mass when it gave off that energy. And when you calculate exactly how much mass it had to lose, you guessed it. It is, once again, the total energy of the photons divided by c².
So, we've just walked through two completely separate proofs. What does all this actually mean for how we think about physics? Let's piece this together into a powerful new reality.
This table right here just lays it all out, doesn't it? We have two totally different experiments. They're based on different core ideas from classical physics. One is about conserving the center of mass, the other is about conserving momentum. And yet both paths, built with completely different classical bricks, lead to the exact same universal truth. It flips the entire script on a century of physics education. E equals mc² isn't some surprising, weird consequence of relativity. The historical reality is that the link between mass and energy is a fundamental truth that was always there, waiting to be found inside classical physics itself. It's not a result of Einstein's theory, it's a foundational prerequisite for it. And I love this metaphor. It really drives the point home. We've been taught to think of mass-energy equivalence as this strange attic room in the house of relativity, one you can only get to by climbing the weird, winding staircase of relativistic math. But what if it's not? What if it's the solid concrete foundation the whole house was built on in the first place? Realizing this opens the door to a simpler, more intuitive way of looking at Einstein's work, one that doesn't need to lean on so many paradoxical ideas. And that leaves us with one big, provocative question, posed by the authors themselves. Why do we keep insisting on these complicated, paradoxical derivations when simple, elegant solutions from classical physics gave us the master key all along? Something to think about. Thanks for joining me.